Now on to a real classic in the world of Node.js interview questions. How do you block the event loop? Node.js, as you now know, handles many clients with just a single thread. However, as you also know, it has two components to make it as efficient as possible. The event loop, so the main thread, and a worker pool provided by libuv with multiple threads. If a thread takes too long to execute a callback in the event loop or a task in a worker, it's called blocked. When a thread is blocked, it can't really handle other client requests, leading to poor performance or even denial of service. And blocking the event loop is easy. Just run a synchronous, long-running operation just like the one you see on the screen now, on the main thread. While that code runs, the entire application becomes unresponsive until that code finishes, which highlights the danger of blocking the main thread. So let's take a look at how this works in practice. I'm back here in my course repo. I'll go to blocking the event loop folder over here, and here I've got the script we just saw. Let's copy the relative path. Let's run. And while we do so, let me walk you through. This is a loop that does 10 billion iterations and adds 1 each time it iterates. And you'll notice that first we get line 7 displayed to the console and then line 9. Meaning that until the task of running this loop completes, nothing else will get printed to the console or executed. Now, how would we fix that example? From previous lecture, you'll remember worker threads, and this is exactly what I will use in this case. So just as previously, we've got the file split into two sections, the main thread section and the thread or separate thread section. In the main thread section, we will initiate a new worker, and then I'll send a simple message which actually is not going to get consumed in any way by the worker thread, but it will initiate the process of running that exact same loop and returning the result back to the parent port, meaning the main thread. One important block of code is this worker on message. It will receive the message back from the worker thread, will log it on line 7, but then on line 9, I'll create a timestamp and initiate termination of the worker, and once that is done, I'll print to the console the time it took for that worker to get terminated. This will be to show you the amount of millisecond it will take for Node.js to completely destroy the previously created worker. We know from the previous lecture it took a few milliseconds to create that worker thread, and from this we'll know how many milliseconds it takes to destroy that worker. Okay, let's copy the relative path as previously, and let's see what we get here. So first observation is that the main thread is immediately accessible. That is because we don't have any substantial payload to be passed on to the parent port. We are essentially sending, over here, line 20. We are essentially just sending this start string, which doesn't even get used in any way. All we want to do is to initiate the worker thread to perform this calculation. So that means if we are not passing anything or the payload is relatively small, it will have negligible impact on blocking the main thread. Then, if we take a look at the console over here, the first message is that the task completed in almost 9 seconds. So this is pretty much what we saw from the script running outside of the worker thread. And that is fine. Then we get the message from line 7 over here that the worker thread completed, and we get that number. And lastly, you get this line 10 console log about terminating the worker, and 5 milliseconds later, the worker got terminated. So the actual cost of spinning up the worker and then terminating it is really small, but it's still a few milliseconds. If your system has a very complex architecture and runs multiple resolvers, handlers, stuff like that, those 5 milliseconds to spin up and then spin down the worker add up, especially if that's for every request. So even though this seems to be insignificant, which it is for this simple example, in the larger scheme of things, this could really add up if you do this for every single request. So that's something to bear in mind. Another thing to bear in mind with regards to blocking the event loop is performing JSON-related calculations. I mean, stringifying or parsing JSONs. So in this file, the simple file, I'll have a nested JSON object, which you can see how it's constructed by this loop. It will perform 20 iterations, and on each iteration, it will basically nest some more information inside of this object. And then what I'll do, I'll perform a few operations. I'll perform stringification. I'll search through that JSON object, or rather that string. So this will give us an idea of how much time it takes to find a substring. And lastly, I'll parse this string as well. So let's see how much time does that take. Here's the console running the script. Right, so the stringification took 130 milliseconds. The index of search of the substring took just about 3 seconds. JSON.parse took over 200 milliseconds. So what this tells you is that if you are working with larger JSON objects, this will be a CPU-bound task as well. You need to be conscious of the time it would take to work on those structures. If that is something that you do for every request quite frequently, this thing will add up for your application over time. Therefore, just be sure to use these synchronous APIs on relatively small objects, small strings, and if there's anything substantial, you might start to consider offloading it to potentially a worker thread. But other way that you can block the event loop is by using APIs built into Node.js. Node has several synchronous expensive APIs which could block the event loop. And namely, that's encryption, compression, file system and child process related APIs. In encryption, beware of random bytes in synchronous version without a callback. Random fill sync, which serves a similar purpose, but it fills a buffer to prescribed length, and pbkdf2 sync, which is a synchronous password-based key derivation function. It is often used to derive cryptographic keys for encryption algorithms from a user's password. This is crucial for securing data at rest or during transmission. The next set of blocking APIs comes under the umbrella of compression APIs. So deflate sync and inflate sync are native Node APIs for compressing and decompressing data respectively. In both cases, they accept a buffer with data as input and a set of options. Moving on, there are a few dozen synchronous file system APIs in Node. They, of course, have their purpose, but mostly in scripting or when ensuring execution order. They should not be used during serving client requests on the main thread. Lastly, we've got child process. More on this module later in the course, but for now, let's briefly touch upon its sync APIs. Spawn sync has almost identical behavior to spawn, the difference being it will not return until the child process was fully closed. The use case, similarly to other synchronous APIs, is in automation and scripting, where the program needs to wait until a certain task is completed before continuing. Exec sync has a similar use case. It serves to run shell commands in a child process. The last example of blocking API, exec file sync. It is used when you want to synchronously execute an external executable rather than a shell command and wait for its completion before proceeding.